In this video we're going to explore the concept of a river regime and also a storm hydrograph. We're going to be examining their features and some of the factors that can influence the discharge of a river. It's important that we start by thinking about what we mean by a river regime. A river regime is sometimes referred to as an annual hydrograph, and as that name suggests, it represents the variations in the discharge of a river over the course of a year. So very often it's shown as a line graph, maybe something like we can see on the screen here, and it shows us the discharge and how that varies from one month to the next, giving us a picture of maybe how that river behaves over the course of the year. With the examples that we can see here on the screen, they have two different shapes. The river regime on the left hand side has a relatively flat line. The black line here indicates the recorded discharge of the river throughout the year. We can see that it doesn't vary much between more than 1 or 2 meters cubed per second. Remember, that is our measurement of discharge of a river, meters cubed per second, sometimes also referred to as cumecs. So this river here, because of its underlying geology, it trickles along quite steadily, a little bit higher in the winter months of December and January and February, and a little bit lower in July and August and September, maybe when rainfall is a bit lower or evapotranspiration is a bit higher. This river, on the other hand, which actually isn't too far away from this one, but sits on a different type of rock, we can see varies much more in its regime over the course of the year. So here it's fluctuating from 0.5 cumecs up towards about 5 cumecs over the course of the year. We would say that this regime is a little bit flashier than this one. The one on the left hand side is a little bit flatter and this one is a little bit flashier. When it does rain, the river is responding a little bit more quickly to that rainfall. So this graph gives us an idea about how a river behaves in a typical year. And obviously that's going to vary from one year to the next, depending on how much rainfall there is and how warm or cold that area is in any given year. A storm hydrograph, on the other hand, shows something different. So a storm hydrograph shows us how the discharge of a river responds to one storm or rainfall event. Rather than looking at the discharge over the year, we're just focusing in now on maybe a few hours or a couple of days worth of time and thinking how the river responds to one period of rainfall. This is a graph you need to be quite familiar with, and we're just going to look now at the different components of the storm hydrograph before we start to consider some of the factors that can affect it. So we have two axes on our hydrograph. We have the axis for time along the bottom of our graph, and we have a vertical axis which will measure a couple of things. We'll be measuring on here the precipitation, so the amount of rainfall, and we measure that in millimeters, and we'll be measuring the discharge as well, which is represented in cumecs, or sometimes referred to as meters cubed per second. That's what that actually stands for. A little abbreviation term for that is the term cumecs. Now you notice we haven't got any values on here because this is just a hypothetical graph that we're going to sketch out, but in reality those numbers might vary quite significantly. So the sorts of numbers on the graphs we looked at earlier were between kind of 1 and 5 meters cubed per second, but when we think about much bigger rivers we could be getting up into the hundreds if not thousands of meters cubed per second. There are two main things that we represent on a storm hydrograph. One of those is precipitation and the other is discharge. Precipitation is indicated on our hydrograph with some bars representing the amount of rainfall. So we can imagine here if we had one bar showing the amount of rainfall that fell in the first hour of that rainstorm, and then we could think about maybe in the second hour that rainfall gets a little bit heavier, and maybe in the third hour it starts to ease off a little bit, and then after the fourth hour that rainfall comes to an end. So we can see this pattern of the rainfall increasing and decreasing. Now, an important bit of terminology here is the term peak precipitation. This is the point when the rainfall is at its highest, okay, at its most intense. So this point here, this would be our peak precipitation. Most rainstorms might follow this kind of pattern, that they start off gently, they get a little bit heavier, and then they ease off. So bars represent our precipitation. Our discharge is represented as a line graph. So we would expect that following this rainstorm, the discharge of the river is going to rise, it's going to peak, and then it's going to fall again back to its previous level. So we get this kind of almost like a mountain-shaped curve in this instance. The point where the discharge is going up on this line, we call this the rising limb. That's a term you might come across, and certainly a term that you need to be able to use in relation to a hydrograph. So this rising limb here is quite steep. The discharge is rising quite quickly. This bit here where the discharge is falling, we call that the falling limb. Sometimes you might come across that referred to as the recession limb as well, but the falling limb is probably the most common term that you'll see used. And just like we had a peak in the precipitation, at this point here we have another peak. We have what we call the peak discharge, which is the point when the river's discharge is at its highest. When we have the most amount of water in the river's at its highest point, and then the discharge will start to fall as that water is moved out to sea. Now you'll notice if we follow up from this peak precipitation, we imagine where that falls within our timeline here, we can see that we've got a little bit of a gap between when the rainfall is heaviest and when the river is at its highest. And this time delay between the peak precipitation and the peak discharge, we call this the lag time. Okay, that is the difference in time between when the rainfall is heaviest and when the discharge is highest. The reason this happens is because that rainfall has to find its way into the river somehow. Unless those raindrops are lucky enough to land straight in the stream, they've got to find their way into the river, either through the soil or over the surface or through drains. And it's going to take some time for that water to filter through the drainage basin and end up in the river. So the lag time can be several hours for a small river, maybe up to even a few days for some of the world's largest rivers. In this instance, if we were to try and calculate what that lag time was, we can see here that, let's say for argument's sake, that peak precipitation has occurred about 1.5 hours after the start of the rainstorm. Okay, and let's assume also that peak discharge has occurred, we'll call that 7 hours after the rainstorm. So simply to calculate the lag time, we just work out what the difference between those two numbers is, which is 5.5. So in this case, the lag time is 5.5 hours. It's taken 5.5 hours for that river to reach its peak discharge. A couple of other points to be aware of when we think about hydrographs. One of those is thinking about where this water's come from. So sometimes we separate off the bottom of our hydrograph like this with a little dotted line, and we refer to this bit underneath the hydrograph as the base flow. Okay, and the base flow is all of the water that's getting into the river through the groundwater. It basically kind of shows us what the river would have done had we not had that rainfall. Had this rainstorm not occurred, the chances are that discharge would have just trickled along at a fairly steady rate, because the water being fed in from the groundwater actually takes a long time to get into the river, and it feeds in very slowly. All of this bit above the base flow, this is what we refer to as storm flow. Okay, this is all of the water that is reaching the river either from through flow, which is the movement of water through the soil, or the water reaching through surface runoff. So in this case, we can see that actually, as a result of that rainstorm, we actually have quite a large amount of storm flow. All of this extra water here has been added into the river because of that rainstorm. So we can see that this rainstorm has produced quite a steep rising limb, a relatively short lag time, and quite a lot of storm flow. So it's important that we're able to use these terms like peak precipitation and lag time and peak discharge when we're considering maybe how rivers respond to rainfall. It's important that we're also aware of the different types of hydrograph that we might see within a river, and also the factors that can affect the discharge. There are basically two types of hydrograph. We have flashy hydrographs and we have flat hydrographs. Now, a flashy hydrograph is one that might look a little bit like the one we've just drawn actually. It might have quite a steep rising limb and quite a high peak discharge and quite a short lag time. Essentially, we're getting lots of water into the river, and that water is getting in there quite quickly. Whereas with a flat hydrograph, it might have a shape that looks a little bit more like this. A much longer lag time, a lower peak discharge, and a more gentle rising limb. So here we've actually got less water getting into the river, and it's got in there more slowly as well. So we've got less water getting into the river more slowly with a flat hydrograph. And this can be caused by a number of factors, and very often a bit of a combination of several factors. The first one is the gradient of the land surrounding the river. If we have quite steep slopes, the water is going to run down them very quickly through surface runoff, and it's not going to have a chance to infiltrate into the soil. Whereas if the ground is flat, we're more likely to have that infiltration happening. And as soon as we can get infiltration to happen and the water can end up in the soil, it's going to take longer to get to the river. So a flashy hydrograph might be caused by somewhere with quite steep topography, quite mountainous, hilly terrain, whereas flat agricultural land might produce a flatter hydrograph. Another important factor is the geology that sits beneath the river and beneath the drainage basin. Where the rocks or the soils themselves are impermeable, as in they don't allow water to pass into them, what we're going to end up with is the soils filling up very quickly if the rocks below them are impermeable. That means the soils are going to become saturated, and surface runoff is going to happen more readily, and that's going to quickly transfer lots of water into the river. Where the rocks beneath the soils are permeable, the water is actually able to pass from the soil into the rock below. It's a little bit like having the taps on in your sink, but having the plug of your sink pulled out. The water comes into the sink, but it can also get out the other end, so your sink doesn't really fill up. So that's what happens when we have permeable rocks. That means that the soils are not going to become saturated as easily, and therefore we're more likely to have water moving to the river through the process of through flow, which is going to be a much slower transfer of water to the river. The land use around the river can also make quite a significant difference. So where we have urban areas, we tend to find flashy hydrographs. That's because urban areas are covered in lots of impermeable surfaces. Concrete and tarmac and roof tiles, they all encourage lots of surface runoff. Whereas in rural areas, where we perhaps have farmland and fields and trees, we're encouraging much more infiltration of that water. The other thing that we have in urban areas are drainage systems which transfer water from our streets directly into rivers. So when it rains, that water that collects in drains on the side of the road, the edge of the pavement, that ultimately is channeled straight into rivers, and they become like a motorway to get that water away from the streets and into the rivers nice and quickly, which is good for us because our feet don't get wet when we're walking around, but it's bad for the hydrograph because it means that that water is going to end up in the river quickly, and we're much more likely to get a flashy hydrograph rather than a flat one. Another thing that we can associate as being different between urban and rural areas, which leads us on to our next point, is the amount of vegetation. Where we don't have much vegetation, we're much more likely to get a flashy hydrograph, and that's because the leaves of the trees are not there to intercept the rainfall. Where we do have lots of abundant vegetation, what that means is the leaves are going to be catching the rainfall, they're going to be intercepting it, and they're going to be slowing down the time it takes for that water to get into the river. Trees also perform another important function in that they hold the soil together, so their roots bind the soil together and increase its capacity to store water, and they also help to return some water back to the atmosphere through transpiration. Where we don't have those trees, that lack of evaporation and transpiration and interception means that we're much more likely to get a flashy hydrograph. Another factor is drainage density. This is referred to as the amount of rivers and streams on the surface of a drainage basin divided by its area. So in an area of high drainage density, we'd have lots of rivers and streams in a small space. These rivers and streams, these little tributaries that might be joining onto the main channel, they again act like motorways to move that water very, very quickly into the main river channel. That means that the rain that falls doesn't have to travel very far before it ends up in a tributary and gets then whisked very quickly into the main river channel. Where there's a low drainage density, any rainfall might actually have to travel quite some distance through the soil and groundwater before it reaches a river, and therefore it's going to take longer to get into the main river channel, and we're more likely to end up with a flat hydrograph. High drainage density is most often associated with impermeable rocks. Because the rocks are impermeable, that water tends to stay at the surface. Where we have permeable rocks, that water doesn't tend to stay at the surface, and so we have fewer rivers and streams. Another factor is obviously the intensity of the rainfall itself. If the rainfall is very heavy, we get a lot of rain in a very short space of time, that water is not going to have time, or the soil is not going to have the capacity to infiltrate that water quickly enough. So the water is going to end up sitting on the surface or running over the surface, and that's going to again transfer it into rivers relatively quickly. If the rainfall is spread out over a longer period of time, the soil's infiltration capacity isn't reached. It's able to soak that water up slowly, and then the water stays in the soil and makes its way into the river via through flow, or makes its way into the groundwater. So if we have a short burst of very heavy rainfall, that can often overwhelm the river and the soil, and we end up with a flashy hydrograph. Another important consideration is maybe what the previous weather conditions have been like leading up to the storm event that we're looking at. So where the previous weather conditions, sometimes we call these the antecedent conditions, where they are very wet, the soil's going to become saturated. That means that it simply hasn't got any space to absorb any rainfall from the next rainstorm, and therefore surface runoff is likely to happen, and that water is going to end up being transferred to the river quickly. If it's been relatively dry beforehand, then we might have a bit of a soil moisture deficit or sort of dry soils that are going to allow water to infiltrate them because they've got some space. Other factors as well can come into play, such as if the ground is frozen, it's going to become impermeable, or if it's completely baked hard by weeks and weeks of very, very dry conditions, very intense sunshine, then that can also lead to there being a flashy hydrograph. As we can see, there's a lot of factors that come into play to determine whether a hydrograph is likely to be flashy or flat, and any drainage basin is made up of a combination of these factors. So in summary then, a river regime represents the discharge during a whole year, whereas a storm hydrograph represents the discharge of a river during one storm event. And those hydrographs can generally be characterised as being either flashy or flat. There are numerous factors that affect the discharge of a river, some of them natural factors, others human factors. And those factors are often very interlinked with each other. Flashy hydrographs tend to occur when we have steep slopes with thin or saturated soils, or perhaps in areas where we have a lot of urbanisation, or where there are impermeable surfaces and a lack of vegetation. Flat hydrographs, on the other hand, tend to occur in areas where there are perhaps more vegetation, rural areas, or where there are dry soils which are able to store that precipitation, and that water is able to make its way more slowly into the river channel.